Everyone, good morning guys. Welcome to Rasayan Academy once again. Guys, we are going to study two very important name reactions in the series of name reaction. The first one is Barton McCombie Deoxygenation. As you know, Barton reactions will include radicals, right? The radical name reaction, and it is often confused with the Chugave elimination, okay, because the substrate or the starting material is the same, but it is a radical process, not the elimination reaction, right? So if you have not seen the Chugave elimination reaction video, please see it. I'll just put up a link over here, okay, and then you can compare nicely. Alright, so the first thing guys we are going to study is what is the Barton McCombie deoxygenation reaction, and then we will see some nice examples, and finally we will see how and when it has been asked in your CSIR or GATE exam. Okay, so let's begin quickly. First thing guys, Barton McCombie deoxygenation is a very simple reaction. Deoxygenation, as the name says, is removing the oxygen of alcohols by means of radical fission of their corresponding thiocarbonyl derivative. Alright, so let's say I am starting from this alcohol. This is my secondary alcohol over here. Alright, 2-propanol. I am starting and forming the thiocarbonyl derivative. This thiocarbonyl derivative you must have seen to give elimination also. First of all, you provide a base, sodium hydride or any other base which is going to alright. After that, you provide carbon disulfide. Second step, you provide carbon disulfide, and in the third step, you will provide the methyl iodide. Okay, so what happens is the alcohol, first of all, alcohol is going to be deprotonated in the presence of sodium hydride, and it is going to attack the carbon disulfide. The one of the pi bond will open up, and after opening up it's going to attack on the methyl, so that you get this molecule. What is it? Your thiocarbonyl. All right, there's a sulfur over here, so your thiocarbonyl derivative of the alcohol. Now to this molecule, right, this part is the same as to give elimination. This is first of all formation of the xanthate. Okay, we also call it the xanthate. Xanthate ester formation. Xanthate ester formation. What can we do with the xanthate ester? We can do elimination, that is going to be your syn pyrolytic elimination, that is called to give elimination, or here in the presence of a radical combination we can remove the whole oxygen and remove this whole group and put up a hydrogen over here. You can see I have removed this whole group and put up a hydrogen over here, right? So let's see how is the radical mechanism happening, radical scission happening. Okay, so guys, if you have not yet subscribed to Rasayan Academy, please do, because here you get a lot of content on organic and inorganic chemistry, right? And I'm also trying to make practice sessions for all of you, which are going to come really soon. Also, I am teaching full time on an academy as a CSIR educator. If you want, you can join me over there as for a lot of free as well as plus content. Okay, so let's continue our discussion and let's talk about the first thing, AIBN. What is this? It is your azo, or you could say 2,2 dash azo bis isobutyronitril. Azo bis isobutyronitril. Okay, what is that molecule? The azo molecule, which is going to have bis, that is 2 isobutyronitril groups connected like these. Now, in this is basically a radical initiator. AIBN is your radical initiator because in the presence of heat or light, it is going to give you radicals this way plus nitrogen gas elimination. Alright, so I hope that you are getting the mechanism. It is just a radical initiator, just like your benzoyl peroxide, okay, and it's going to generate this radical. Now, after the radical generation, It is going to attack on the tributyl tin hydride. Yes. So N is for normal butane. Okay, it is going to capture this hydrogen from here. It's not a proton, it is a hydrogen. So it has taken away the hydrogen. So the work of this molecule is done. Plus you generate radical. Alright. So this is the work of the radical initiator to generate a tin radical so the tin can attack on the xanthate molecule. Okay, let's see how it is doing so. Alright, so I'm erasing all of this. I hope that you have written it down if you are noting it down. So I need the tin radical. Where is the tin going to attack? Definitely on the soft center, also the more electron rich center right over here. This bond is going to open up, and see guys, radical mechanism always written in the fish hook arrow like this. Okay, so I am going to write then Bu3. Alright, so this is what happens. Okay, you are getting this radical over here, and the tin has attacked on the sulfur, not on the carbon, on the sulfur. Alright, soft interaction, better interaction, and now this molecule can take away a hydrogen, tributyl tin hydride molecule, give you the product, and you have the tin regenerated. But what about this molecule? Yes, what about this molecule? What happens is this is going to break apart from here, okay, and you are going to get COS, that is carbon dioxide having one oxygen replaced by sulfur, plus you have the tributyl tin SME, right? So tin is connected to sulfur still. Soft interaction is better. You are getting this as a byproduct, and yes, this is your major product. So what have we done? We started from an alcohol in this way. Here 2-propanol. We started from 2-propanol, and then we made the xanthate ester by sodium hydride, by carbon disulfide and methyl iodide. We made the xanthate ester, followed by the radical mechanism. We have completely removed this oxygen and the whole group, deoxygenation. This is deoxygenation, right? We have done that, and these are your byproducts. Okay, very simple and plain reaction. Let's see some examples of it. So guys, the first example that you see is over. Now what do I have? ये देखो, I have AIBN. Once again, this is your radical initiator, but this time you don't have the tributyl tin hydride. You have 2-butyl and 1 chain molecule. It could be as long chain as possible. We don't have to worry about it because we just need our tin radical that we are going to get in the presence of AIBN. Okay, so the tin radical is going to attack onto the sulfur once again. This bond is going to open up. What can you write? The whole reaction is not going to affect any other functional group. Acetals are acid and base sensitive, more acid sensitive. Yes, so it is not going to touch the whole group. This is a radical that you get. Oxygen, double bond C, double bond S, like this. Okay, or let's say here you are forming oxygen, double bond carbon, single bond S, R3, and your OPH is over. Okay, so your major product is going to be this radical taking away a hydrogen from the same source. So I can directly write hydrogen. There will be 2 hydrogens, right? So you started, maybe in the question you start from an alcohol, maybe sometimes you don't start from an alcohol, but you have to identify what we are going to do next. So once again, look at the example number 2. You have two big acetyl groups. You have one alcohol and one protected alcohol. We don't want this alcohol to react. So what are we going to do? NaHCH2 MEI 80%. That is the first step, gives you 80% of the xanthate yield. The first step of the reaction that gives you okay, all the groups as it is. This is your oxygen, sulfur, SME. You are getting 80% of the yield of this product. Further, in the same reaction combination, you are just going to remove the oxygen completely. There will be a hydrogen and one more hydrogen was already there. As it is, everything is as it is. All right. Okay, so this is your product of the deoxygenation. Remember, when we are talking about deoxygenation, we are removing the alcoholic OH group. Okay, very nice examples, guys. Let's look at a similar name reaction. You can compare both of these as well. This is your Barton radical decarboxylation. Okay, so this is not your alcohol removal, it is the carboxylic acid group removal. Okay, so let's first talk about this. The radical decarboxylation. So yes, guys, you do the decarboxylation in the presence of a base also, KOH. Okay, but this is radical decarboxylation via corresponding thiocarbonyl derivative of carboxylic acid. This is super important. Thiocarbonyl derivative. Let's see what is it talking about. So let's say you started from this COOH, RCOOH. How do you convert to RCOCl? By plenty of methods, by SOCl2 or PCl5. Alright, something like that. You can just convert the RCOH into RCOCl. Alright, you have done that. Now, this molecule is going to attack. The bond opens up, falls back, and the Cl minus is going to leave. Okay. What do you see? It is attacking from the oxygen. It is not attacking from the sulfur. Please remember this very important information. Sulfur is a soft center, and this carbonyl carbon, which is connected to Cl, a very good leaving group. This is a hard electrophilic center. Okay. So only oxygen is going to attack you, right? Chalo. So what happens is you are having the two ester formation, thiocarbonyl derivative. Alright. And once again, once you get this ester, इसको हम बोलेंगे Barton ester. Barton ester. Alright. Now we want to see how the Barton ester reacts and gives you the RH. Okay, so let's write the same ester on the back slide. Okay, alright, there it is. Once again, guys, you are having under the same combination, tin radical is going to be generated. Let's say have the tin radical generated. Okay, this is what you have, let's say. Alright, so sorry, this is going to be a radical over here. Going to be a radical over here. Okay, now if we just try to switch these bonds on this side, okay, which means just see where the radicals are moving. It's a very fast process, okay? It's only taking time while I'm writing. Alright. So this radical is right over here. Now what is this radical going to do? This radical is going to force the removal of CO2 minus CO2. Please see how this has happened. This bond, every bond is opening up to give one electron on the left and the right hand side. That is basically one electron on both the atoms. CO2 plus, alright, you have one double bond over here as well. So it is pyridine, completely aromatic. This is your byproduct of the molecule. Have CO2 eliminated, your alkyl radical. So alkyl radical can directly go to the tin hydride in the molecule which is present in the solution, and it can directly take away a RH molecule. Alright, so this is your RH followed by your tin radical that you will be getting. So the tin radical will further be used in the reaction with another molecule. Okay, so it's basically regenerated, not a problem at all. Okay, so this is your answer. This is your alkane that you are getting, right? So radical decarboxylation via corresponding thiocarbonyl derivative, which also known as the Barton ester, and this is the reaction of the carboxylic acid. Now see, let's see examples, guys, because in the examples you will know what are the variety of questions which are asked. See, here your in this molecule, the only group which can react is your carboxylic acid. Here directly carboxylic acid is not given. First of all, COCl whole twice is given. That is, you are supposed to convert the COH into COCl. How are you going to do that, guys? Alright, is it like this? Yes. So what is going to happen? It's going to attack on the carbonyl. The bond opens up, fall back. Cl minus is going to be eliminated. Yes, you are having OH. This way, there will be a positive charge. Cl minus is going to attack on this carbonyl, and the bond is going to open up. So you get the acyl chloride RCOCl plus one atom hydrolyzed for this carbon. Alright, guys, so this is just the mechanism for the conversion of your acid to acyl chloride. Let's not worry about this. Let's worry about what are we going to do by this. See, you have a negative charge on oxygen. So let's say even if you're acid, I'm only writing this part because only this part is required. Okay, only writing these two rings. I'm only writing this part of the molecule, not writing. The COCl is going to be attacked by O minus. There's O minus and the Na positive over here. So the O minus is going to attack over here. Cl minus eliminates, and you are going to get the first molecule. Okay, you are going to get the first molecule, double bond O. Now, yes, guys, you do not have the tributyl tin hydride and AIBN combination. So, what are we supposed to do? You only have heat. Presence of heat, you say, कि चलो ठीक है, radical mechanism is possible, but what will happen is the bond is going to open up in this way, like this. All right. So the sulfur is going to be connected through this molecule, oxygen minus CO2 has already happened from here, and the sulfur is connected to which, alright, to which this molecule is connected. And what do you have now, guys? Since the bond has fallen over, you are having all aromatic system. Right, so this is your molecule. When you do not have the AIBN and isobutyronitrile combination, you are just going to write it in this way. Okay, this is very very important. In the presence of heat, this whole group is not eliminated but just going to stick over here. Alright, and then you have metachloroperbenzoic acid. So what is that going to do? It is going to do the self oxidation, metachloroperbenzoic acid heteroatom oxidation. Okay, then 100 degree centigrade 78%, मतलब कि ये हो जाएगा elimination. So alright, so elimination is going to, right, which kind of elimination? ये देखो sulfoxide elimination, sulfoxide sin elimination. Just like your selen oxide, you also get sulfoxide and sin elimination, where from the methyl group which was present over here, this little one you see, the hydrogen present on the methyl, and it is going to be going to eliminate like this. Okay, this way. So yes, we are done looking at this example. Also, let's look at a question or more than one question. See this one. The most suitable reagent combination to affect the following conversion is. Okay guys, so check out the question by yourself first and then I'll tell you the answer. Okay. First thing, what do you notice? You have removed this OH. Yes, and there are only two hydrogens over here, nothing else, no functional group, rest of the molecule as it is, right? So which means I have just converted the OH group into my xanthate, sodium hydride CS2 methyl iodide. This combination is for the xanthate formation, xanthate ester formation. Okay, this carbonate, this, yes, all of this combination is for the radical reaction. Okay, yes, this combination is for the radical reaction, removal of the whole xanthate group to give you. Okay, already one was there, one more has been added. This is your final answer option. That you are going to take this combination to give you the very simple Barton McCombie deoxygenation reaction. Okay, chalo. Moving onwards. Okay, guys. So these reactions could be really difficult to remember. If you keep on revising and practicing the previous year questions, you will be able to do so very easily. Now, the intermediate A and the product B formed in the following reaction are. So this is a CSI net question. Okay, so this is a CSI net question. What is the question asking you? See, you have some ring over here. This ring is going to attack COOH. Previously, if you have seen, previously if you have seen the Barton radical decarboxylation method, here you saw that, ma'am, you are not taking the acid directly, you are converting this to acid chloride and then this group is reacting, isn't it? So that's one way of forming the ester. This is your ester group, right? This is one way of forming the ester. Okay. Another way of forming the ester is taking another chlorinating agent. Once again, you are converting this into acyl chloride only. Converting into acyl chloride just with a different reagent. However, the last example that we do, this is DCC and DMAP. So DCC and DMAP are used for coupling reactions of carboxylic acid as well as the usually the alcohol, but here you have the O minus over here. All right, phenolate. Okay. Right. So we are going to do the combination of this directly, coupling reaction. Okay. You have this oxygen connected to nitrogen, a ring All right, let's directly write the sulfur double bond over here so that you can double bond maybe on this side. Okay, yes. Now what was there in this ring? All right, nothing at all. First of all, you have formed the ester, no problem. Now in the next step, tributyl tin is going to attack over the sulfur and it's going to be a single-headed arrow. All right, yes. This Now what will happen? This bond is going to open up, fall in such a direction. Okay, this is your CH3, all right, hydrogen over here. So what do you get? Once you are breaking out the whole thing, you are breaking out the whole carbonyl molecule. You only one radical over here. What about the other part? The other part is going to be alright. So the only yes, the other part is going to be like this. Have minus CO2. CO2 is eliminated from this molecule. Alright, and then you have this reagent. Okay, yes. Radical going to do? Do you have a radical source? Yes, you do have a radical source, and the hydrogen source is pyro. I have drawn. Alright, so be careful about these little things. Guys, deuterium is going to add in whichever way it want to add, above or below. Since it is a radical, it can also give you 50%, no problem. So option number A and B are absolutely wrong because they are connecting the carbonyl with sulfur. That's not going to happen when the O minus a hard nucleophile is present. Okay, that's not possible. So this carbonyl carbon and the oxygen are showing a hard interaction. That's why this is your stable species, followed by the N-bu tributyl tinhydride to give you the okay. The D is coming from the tributyl tinbutyride. All right. Previous question was on the Barton McCombie deoxygenation. Okay, this was on the Barton McCombie deoxygenation, and this reaction is on the Barton radical decarboxylation. Okay, so basically, guys, plenty of new reactions are going to start up once again. And if you have not yet followed, please follow on Rasayan Academy. Please subscribe if you haven't already. Also share it with your friends. These are important series. I will be starting a practice series for the previous year net and gate questions very soon. So what you have to do is just see the previous year questions and then start solving. Okay. So, alright, guys, I will see you in another such session. If you are liking the session, please subscribe and also press the bell. Alright, guys. Bye, everyone. Have a nice day.